Today we'll take a look at domain and range symbolically as opposed to graphically like we saw before. Remember, the domain of a function includes the set of all the possible input values for the function. So for example, the natural domain for f of x equals x squared would be all real numbers. The range of a function, remember we said, is the set of all the output values that would come from an input value. If we were looking at x squared, remember the range would include only 0 or positive numbers there. So it would go from 0 to infinity. We'll spend most of the time determining domains. So to decide what the natural domain of a function is, using symbols, looking at a function notation, there are a few things to look for. Division by 0 is obviously a problem. We know that doesn't result in a real number. Also, taking an even root, like a square root or a fourth root of a negative number, does not give a real number either. That doesn't exist. So that's something else to look out for. Lastly, logarithms of negative numbers don't exist either. We'll talk more about logs later, and those don't come up very often, but remember there is that restricted domain there too. So to deal with these problems, basically just look for those situations in your function, and if they exist, set up an equation or an inequality to describe what's happening with the domain based on those concerns, and then solve those inequalities to see what the domain should be. So let's try a few. Looking at example 1, we've got 4 functions here. We want the domain of each. F of x is a linear function, 3x plus 2. There is no division by 0, no roots, no logs. There are no restrictions here. The domain would be all real numbers, negative to positive infinity. For g of x, we have the square root of x minus 4. This time, no division, no logs, but there is a radical, so we need to make sure for that even root, we need to make sure that x minus 4, the radicand, the piece on the inside, has to be not negative. It has to be greater than or equal to 0. You can solve for x easily, just add 4 to both sides. We know that x has to be greater than or equal to 4. That describes the numbers that work for the domain, the x values that are okay. So we can use 4 or any number bigger than 4 in our domain. So we would start at 4 with a bracket and go to infinity. You could test it, any number less than that won't work. You'll get a root of a negative. For h of x, we've got a rational function, 6 over x minus 5. We're dividing by 0. That's the problem here. There are no radicals, there are no logs, but there is one value of x, and you might be able to see it, where we could end up dividing by 0. To find out where, make sure you can set up an inequality. X minus 5 cannot be equal to 0, so add 5 to both sides. That means that x cannot be equal to 5. You might have been able to see it, but we have to take the single number 5 out of the domain. Any other x value is fine, but 5 will not work. So we have to write 2 intervals, one on the left side of 5 and one on the right side of 5. And this is the way to do that in interval notation. We go from negative infinity up to 5 as an open interval, not including 5. And then we skip over 5 and we start on the other side of 5 and go from 5 to infinity, not including 5 there either. That includes literally every real number except for 5. Let's take a look at that last one, j of x. We've got the cube root of x function. Tempting, but there are actually no restrictions here since it's an odd indexed root. The cube roots are fine. Remember, we can take a cube root of a negative number. Cube root of negative 8, for example, would be negative 2 because negative 2 times negative 2 times negative 2 gives negative 8. Since we have an odd number of multiplications there, it's okay to still have negatives inside. So the domain would be all real numbers there too. Example 2 is a bit tougher. This k of x function is x minus 5 over the root 3 minus x. This time, x minus 5 in the numerator is okay. That might be worrisome, but that doesn't cause any domain problems. But there are some domain issues coming in the denominator, right? First of all, we can't divide by 0. So that entire denominator, the square root of 3 minus x, cannot be equal to 0. You have to solve that inequality to see what x value would make that happen, or maybe you can see it. This is a pretty straightforward one. If you square both sides, add an x over to the right side, flip it around if you want to, we'd say that x cannot be equal to positive 3. Choosing x equals 3 would cause us to divide by 0, so it's got to come out of the domain. The other issue that we have here is the square root, right? Regardless of the 0 denominator issue, this radical cannot have negative numbers on the inside. So 3 minus x needs to be greater than or equal to 0. So we can add an x to both sides again. We can flip it. Don't forget to flip your inequality sign there too. X has to be less than or equal to 3 in order to make this work. So tiny discrepancy there, right? X less than or equal to 3 technically does include 3, but we said earlier that we can't do that. So we need to remove 3 from that last inequality, so we would write x less than 3 instead. Write that in interval notation and you're done, right? The domain would go from negative infinity up to 3, but not including 3. Again, you could test it. Pick a number less than 3 and it'll work. Pick a number bigger than 3 and you'll have the radical of a negative down there. Let's look at one example of how to deal with range symbolically too. This is a less common thing to have to do. It's a lot harder, I think. You need to look for trends that exist within the given function. So look for max and mins, increasing or decreasing, all those sorts of things we've studied before. And also think about the function type and the transformations that might be applied to it to help think about what the range would look like too. So imagine this one, x squared minus 4. X is always going to give something that's not negative, right? When we square a number, that number is going to be 0 or larger as a result. So if we were just looking at the function x squared, the range would be 0 to infinity, including 0. But that minus 4 is a shift downward by 4 units. That's subtracting 4 from all the outputs. That's decreasing all the outputs by 4. So actually, the lowest that we could get is negative 4 in this case. So the range would be negative 4 to infinity. Oh, whoops, that one popped up early. So we've got the square root of x minus 4. Notice I've got the domain written the same way there. You can, that's a reminder from last time. But we'll look at f, g, h, and j. So f of x, that linear function, it's got opposite infinite in behavior. On the left side, it's going down towards negative infinity. On the right side, it's going up towards positive infinity. So there are no restrictions on the range for f of x. That thing is going to hit all y values. The range is all real numbers. Back to g of x, we said that earlier the domain was 4 to infinity, excuse me, which is going to cause the range to be not all real numbers this time too, right? So we know that our lowest x value that we could have is 4, and we know that this square root function is an increasing function. Right, it looks something like this. It's going to keep increasing off to infinity. So what we need to do is plug in that lowest x value to see what the lowest y value would be. Plug in x equals 4, we'd get 0. And so that means the range would have to go from 0 up to infinity. For h of x, take a look. We said the domain was everything but 5. That is, as we mentioned, a rational function. We know what that looks like. It's going to approach at that x equals 5 vertical asymptote. We know that it's going to approach infinity on one side and negative infinity on the other. So it'll look something like this, right? So looking at that piece alone, we're going to hit all those y values, except for maybe the horizontal asymptote value at y equals 0. And you can kind of test that too, right? I'm claiming that we're not ever going to get a function output of 0. You can't divide 6 by anything and get a 0 as a result. And to prove that, right, we could set that up as an equation, set the output equal to 0, multiply x minus 5 on both sides, you get this equation, and you get the equation 0 equals 6, which is obviously not true. So that means that the output cannot be 0 here. That's a little strange, that you don't have to do that often. But the idea is that the range is going to include all real numbers except for 0. Right? We know it's going to go down as far as we want it to, up as far as we want it to, but the function will never actually hit that horizontal asymptote value of 0. Lastly, j of x, again, there are no restrictions. This is an odd root. That function is going to continue down. The range would be negative to positive infinity there too.